All right. Good afternoon, everybody. It's 12:05 for me, so afternoon it is. We are starting the new unit on quadratics, chapter 3 of the book that I've gone through in the past or used in the past. Doesn't really matter to you, I guess, because you just get handouts and everything. So we're going to look at quadratics. Maybe I'll start out with another example of nets and patterns drawn to scale, just to make sure you're good to go with that stuff. So these different looking Kleenex boxes, you Google like triangular Kleenex boxes or watermelon Kleenex boxes, they come up. I haven't seen them in stores, but apparently they exist. If you were to do a net for those, let's go through the idea of doing a scale drawing net of these. So the drawing is going to be centimeters, or in this case on the screen, squares. Make it easy. RS, I guess. Anyways, and so 3 centimeters on the object would be the number of squares on the drawing, right? So we're going to use the scale to calculate things out. Let's just think about the general idea of the net first. Picture this rectangular bottom, right? We just show the rectangular bottom kind of like that. You could picture the triangle sides folding down like that, and then these long edges folding out. So the net's going to be something like this. So just visualize that first and then try to calculate all the numbers for things, right? So let's move this over to make room for calculations on the side. For me right now, you can just do them on a separate page or whatever, so you have lots of room for your graph, your pictures. So let's look at each number here. We have our scale of drawing to object. This is what you want to do when you're doing this. Drawing to object, you have your 1 square to 3 centimeters. And then if we wanted to get, say, this length right here, the 10, which is going to correspond to that one right there, right? So we have our 10 centimeters of the object, and then we're going to calculate how many squares we need to make that thing. So the process here would be, like we said before, second divided by first. So second divided by first in this case would be 1 divided by 3, right? So we're multiplying by a 1 over 3, which is the same thing as dividing by 3. So we just divide 10 by 3, we get our 3.33333, right? So we're looking to have this side be 3.3 repeated squares, basically wide. So it looks like I'll probably have lots of room, but maybe I'll do a bunch of calculations first and then decide how much space we need on the graph. Should be fine if I put it in the middle though, right? So let's just do that. Way to the middle here and have width, at least I'll establish a width of 3.3. So about like that. And there's the 3.3 representing the 10 centimeters. And let's do the 9 as well. So if we did you could even just do this where you write, say, for the next one, say 9 centimeters, and do the same thing, obviously, the multiply by 1/3. It's easier in this case because 9 divided by 3 is just 3. So we have a 3 squares, right? So that is the other dimension. So this one here. So this one went in as 10 and the 3.3. This one's representing the 9 and the 3. 9 centimeters, 3 squares. So on my net, down here, I can go up 3 squares. Something like that so far. I would use a ruler, but it's awkward on a smart board because the ruler touches the screen and so on. Could use the line tool, I suppose, from now on if you want to. I want to motivate you or suggest that you probably should use a ruler, right? So if I did this maybe right now just to touch it up, make it look a little nicer, but little things like that happen to make this annoying. Jumps around on me, but here we go. Hopefully Yeah, you know what? I think you can see why I shouldn't do that. Let me just erase that and see how it's just hard to line up the edges and so on, right? So let's just stick with decent hand drawings for this, for my version at least. Right, so that's good there. And then the other values here, the 13, for example. So the 13 is going to be some number of squares this way. Right, so I'll figure that out and then show that. Probably can do better on that one. Right, so I'll get that value. So 13 centimeters going to correspond to a certain number of squares. So times 1 by 1 over 3 again, the way this is working out. So 13 divided by 3, 4.333. So 4.3 repeated again. So shot the mark here a little bit, or not. 1, 2, 3, 4.3. So just a tiny bit. Third of a square there, right? It off. And then the other one's obviously the same. So let's show this as the 13 centimeters here, or 4.3 squares. And the same on the top. So 1, 2, 3, 4.3, 4.3. We got that. And then we need to get the triangle part made. So let's do an extra calculation here to do a good job. We really want to know how far out to go there. And then the diagonal will be this, this matching 13 size, right? So we're really going to have to do a calculation where we're going to know that this is half of the side there. So half of the 9, not 3. Half of the 9 is 4.5. Do that. There we go. So this would be like a 4.5. And the 13 is known, so we can calculate this unknown, right? So let's do that. Let's make a triangle. I'll move it down there. I'll just draw it right now so it's easy to compare what we did here. So the 13, this number here for that length. And so you're visualizing like this triangle here, right? Where you have the 13 and the 4.5, okay? So that is what we need to do here. All right, so down here, let's calculate that distance, the height of the Kleenex box, really, right? And so you'll remember from previous work, this is a Pythagorean theorem situation where the hypotenuse is 13, so it's going to go in the spot by itself, and the other sides can just go in. So we have that, and so let's do this. We've got 4.5 squared gives us 20.25. And we have the h squared and the 13 squared, just to make sure you get it. You might as well type it in, right? But that's what I was thinking it was. So we have the numbers in there, and so then we're going to subtract 20.25 from both sides. That says 22.5, sort of. H squared is left with that. So 169, take away the 20.25. 148.75. And then square rooting both sides. Technically, plus or minus is, both answers are acceptable, but for a length of a side, we're just going to use the positive case. Root of that thing. Root 12.2 or so, right? 12.19 rounds to 12.2. So we're looking at 12.2 centimeters. And so then we're going to do the same ratio work as before. Maybe I'll just move this down so I can do it where it was, where there make space for it there. So now this new 12.2 centimeters is going to get divided by 3. Divide by 3 gives us 4, almost exactly, really, 4.1. So 4.1 squares. So let's go out 4.1 squares. So let's go from this one first. 1, I suppose I should just count, right? 1, 2, 3, 4.1 or something. Put a dot there. And just draw the lines, really. That line there and that line there. Our Kleenex box. So let's go, 1 step, 2 steps, 3 steps, 4 steps, a tiny bit more. Just the Kleenex box line there. So then you could add on here that this is still, this is representing 13 centimeters, which is that 4.3 squares, hopefully. Repeated squares, and so on. So I'd label more, but that's pretty much it for the job here. If I were to check things here, I could check this line. That's supposed to be at least around that 4.3 size, right? So that should be about the same size as this triangle side, which I think it worked pretty darn good. Okay, so there's a net drawn to scale with all of the process shown and everything else. So as usual, if you were trying to work as an active learner and so on, you might have printed this out and done it yourself and then watched this section of the video for help and so on. All right, so on with the main event here, Quadratics, the new stuff. New stuff for this course anyways. Of course, it's some review of previous courses for you. But let's go through it. So I want to draw attention to the main thing here is that we have this standard form of a quadratic. Okay, so that's the main thing I want to focus on just first. I've got a lot of other things ready to label here, but that standard form of a quadratic is that. And it's called the standard form, not so much because it's the best one or the one to you hope to use and so on. It's more just the fact that it's arranged in order. So it's arranged from highest powers to lowest powers. Let me show you what I mean by that. Just try and cover up some stuff to draw your attention to the parts I want. So this is x to the power of 2 here, right? So we've got an x to the power of 2. And then this one's understood to be a power of 1. It just is, right? So we have an x to the power 2, and then later on an x to the power of 1. I'll put it as dots because it's supposed to be just understood to be there. And this one's even weirder. This one is actually an x to the power of 0. X to the power of 0 is just 1. And there's understood to be a 1c there. Okay? So this really is x to the 2, and then 1, and then 0. Right? But the x to the power of 0 is completely invisible because it just becomes a 1. So I'll just put it dotted like that. So you have ghost exponent of 1 and a ghost x to the power of 0, but really is highest powers to lowest powers is the primary organization. And then also the coefficients. So these ones here, the A, B, C are your coefficients. They are numbers. Maybe I'll get rid of this now and show here that they are called coefficients. And they're just the numbers. And your coefficients are also sort of arranged in order, but the coefficients, so COEFF for short here, are alpha arranged. So that's why it's like A, then B, then C. And that's just the way they choose the letters because they know the order is going to be highest power to lowest power. Okay, so that's just the generic version of things. Oh, and I should point out too the big difference that should stand out to you between the x squared and x versus the blue, like they're in a different color on purpose here, right? And then the blue ABC. the x and x squared are variables. They can take on any value. So you're going to say let x equal 2, let x equal 7, let x equal whatever number you want. Whereas the ABC are just the numbers that you were given. Okay, they're just numbers. So, for example, if you were given an equation y equals 7x squared plus 3x minus 2, then the 7 and the 3 and the negative 2 aren't up to you. They're just in there. And then you're going to choose certain values for x. Maybe you choose a value of x is 1, let's say. So you'd have a 1 squared times the 7, and you'd have a 3 times the 1, and a minus 2, and you'd calculate out what that thing would be equal to, right? You have no choice about the 7, 3, and the negative 2. They're just there, whatever values you were given. The x, though, you choose and you put a bunch of numbers in to get a bunch of corresponding y values. All right, so the simplest version of a quadratic equation is just y equals x squared. And I would like you to just think for a second about, in this equation here, what's the a, the b, and the c? Okay, so press pause if you want to have some time to think about that. But what's the value of the a, the b, and the c? So the a might be a little easier because it might remember that we've talked about how there's an understood 1 in front of everything. So the a is a 1. The b and the c are kind of weird, right? Because what value of b would lead to this and what value of c would lead to that. And the hint would be to recognize that there's nothing here, right? So we have the y equals x squared, and then you have let's say plus nothing, right? And then plus another nothing. And so usually I would say, well, what number represents nothing? Let's just make that a little bit harder to read here, right? What number represents nothing? Well, of course, it's 0, right? And so what you really have there is plus 0x plus 0, right? So the b and the c are just zeros. So just trying to make sure it's obvious what the connection is between the different, the standard form, and then this simplest version of the standard form. I don't want you to think of it as a new and different thing, okay? So plus nothing because of the zeros. Anyways, let's get going then. So let's graph this thing. The scale is going from like minus 10 to 10. We don't need to go all the way, but let's start in the middle at 0. And when we're calculating, we're going to show some work, and I'll show you an option of how to do it with less work shown. That should be pretty doable. So y equals x squared, and we should say, okay, let x equal to 0. Pretty easy calculation. Obviously, the one we're starting out with, we'd have 0 squared, and you just get 0 as an answer, right? So you can say, okay, 0's in there, no problem. And let's keep going. Let's do a 1 and a 2 and a 3 and a 4 and we won't end up going farther than that, and you'll see why. Okay, but technically you might consider going all the way to 10 and minus 10. Okay, so I might shrink this down a little and put on there like ... meaning we could consider doing more. And then we'll also go in the other direction. And we'll decide how far to go in each case as we calculate numbers. So this one's fairly straightforward. I'm not going to do a whole lot of extra work showing, maybe I'll show a little bit for the negative when we get to it. But 1 squared is 1, 2 squared is 4, 3 squared means 3 times 3, so it's 9. You can tell we're at the top of the grid. So if we did a 4 squared, we get 16. And so basically at that point, you're like, okay, well, I'm not going to do that one because it's way off the graph, right? So if we're going the other way, let's do the calculations for an x equals a negative 1. That's going to be a y equals, and I can't write negative 1 squared. I have to write it as negative 1 all squared. Because negative 1 all squared means a negative 1 times a negative 1, which is what it really does mean. So we get a positive 1 as an answer. I'll just write 1 because it's understood to be positive. You don't have to write in the positive sign. Move that up a little bit so it's not overlapping there. Here we go. Whatever. So we have the positive 1. Just note if you wrote it as negative 1 squared, negative 1 squared means negative of this stuff squared, 1 times 1. Think of it as, and so that your answer would be negative 1, and it would be wrong. Okay, so watch that. You have to square, when you're squaring something, it's the thing. So in this case, the -1 times another -1. In this case, too, a -2 times a -2 is going to give us a +4, and so on and so on. Okay, so we got our +4 and our +9, and we're not going to bother with that one because it's going to be off the page, off the graph. All right, so let's graph it. We're going to graph our 0, 0, and our 1, 1, and our -1, 1, and our 2, 4, and our -2, 4, and our 3, 9, and our -3, 9. So we graph that. You say, okay, well, there's the shape we're talking about. Okay, and when we're analyzing that shape, one of the key features is we're going to talk about the shape of it, right? And obviously it's a quadratic shape, but let's analyze the first difference a little bit, and then we'll talk a little bit more about the key features of that shape that make it be that recognizable shape. So if we look at the first differences, pretty easy to see down here that we're looking at up by 1, and then up by 3, and then up by 5, right? Going from 0, 1 is 1, 1 to 4 is 3, and then 4 to 9 is up by 5. So it's a classic 1, 3, 5 shape, and that's what I'm going to show on here. You go over 1 up 1, and then over 1 up 3, and then over 1 up 5. And that's your base quadratic shape. It's your classic 1, 3, 5 curve kind of shape. So, you have this kind of a shape-ish, right? So that's good. It's not like this. It's not like this. It's not, there's lots of it's not like, right? So it's not like that one. It's not like that one, right? Okay, so the quadratic shape is, you want to try and do a good job drawing that kind of shape. So the rest of the first differences here, you can tell someone was down by 1, down by 3, and down by 5. So that certainly is easy to visualize too, where you go down by 5 and down by 3, right? So down 5, down 3, finally the down 1. It's just that same mirror image of that pattern. That's something to watch for in quadratics. It's helpful to know that's going to be the case. Notice, again, I'm just going to mention this 1, 3, 5 is your classic quadratic pattern. So that's sort of the grade 10 and up version of this, whereas the grade 9 version would have just been to say, hey, they're not constant, so it's not linear, right? So this is not constant, so it's not linear. Of course, it's not linear, it's actually quadratic, right? Instead, it's quadratic. All right, so that's good. And then that's our first differences. Let's look at our second differences now. So second differences. Let's look at the easier ones again. Let's look at 1 to 3. It's obviously up 2. 3 to 5 is obviously up 2. From -1 up to 0 up to 1 is obviously up 2 as well. These are all up 2, up 2, up 2. Okay? So now the grade 10 and up version of things is to say, oh, constant second difference. Means we're talking about a quadratic. So you can tell if a relationship is quadratic from the numbers with the constant second differences. You can tell if it's a quadratic from the equation based on it having really the highest power being an x squared. Okay? You don't have to have all the other stuff as long as you have at least that highest power. Then you know it's quadratic. All right, so that's our starting point here. Let's go to key features and then we'll come back to this example. So the other thing you want to watch for as you're doing this is all the key features. So if you look at this quadratic, it's not one of the basic ones. You really probably can't tell me what the equation is for this one. Some of the features you'll see, you're going to be able to figure out based on looking at it, but a lot of the numbers are pretty random and hard to figure out. But let's start out with, of course, the idea that this thing is direction of opening wise, it's opening up. So this one's opening up. Obviously, this kind of a shape would be opening down. Make sure I get what I mean by that. And the shape, of course, it's a quadratic shape, right? So it's quadratic and it opens up. The vertex is a spot we're going to be labeling and noticing. So the vertex in this one is right there. I'll make sure to label it there. And so the vertex is over 1, back 1, and down 4, right? So -1, -4. So that's going to be labeled in there as -1, -4. That's the vertex. Right? Don't think of this as much as like whether something has a maximum or minimum. Some people think about the equation more so, but really just look at this as like we went down, 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 and then back up. We went to a lowest value, and so we went to a minimum, right? So we went down to a minimum value. So it has a minimum, and then the value of the minimum is, of course, that lowest value we got to, which in this case was -4, right? So we say, okay, well, y equals -4. What you're going to notice as you go through lots of examples of these, you're going to realize that the y value of the vertex really is your minimum or your maximum value. Okay? Whatever that y value is in your vertex is your maximum or your minimum. Axis of symmetry. Next. So axis of symmetry, actually remember I have this ready to go here. So axis of symmetry is this mirror image line. You might have played with a mirror in elementary school. So you put the red clear plastic thing, you can sort of see a reflection on there, and you'd be able to see the reflection lies on top of the actual graph on the other side. So you can see through it and see the reflection. It's a physics thing, partial reflections, partial transmissions. Yeah, so your axis of symmetry in this case is these x values are all x values of -1. So this one here is an axis. That's the axis of symmetry. And it is x equals -1. It's just x equals the x value. So we're going to put this in here, x equals -1. And once again, we're going to hopefully notice that we have, what color do I want to do for this? Let's choose some other color. Maybe I'll use yellow. That'll stand out. So the x and the 1. So see how the x value of the vertex is the x of the axis of symmetry. And sometimes you'll have graphs that you can see where it crosses the y-axis and where it crosses the x-axis. Not always. You'll see in your examples. But we can easily identify, in this case, if I get rid of my minimum swoop there, it's a little easier to see that we have a y-intercept of -3. So y equals -3. And the x-intercepts up here. So x-intercepts of -3 and 1. So x equals -3 and x equals -1. Negative and my 3 joined together there. -3 and 1, or -1, right? So I think I'll come back to the equation, yes, but at least the details of it, at least the main form, of course, you recognize the shape of this and so on. So you should be able to at least pick out that it's a quadratic, right? So maybe we'll come back to the rest of that once you've had some experience with it, because I want you to have a chance to go through these examples and see what they all look like, and start to make the connection as to what you can tell from the equation itself. And later on, there's questions about that. Like, what can you tell from the equation? Can you tell where the vertex is? Can you tell where the direction of opening is? And so on. Okay, some of those are yes, some of those are no. And you'll find out as you go and do a bunch of them. So that's this slide here where it's like, you'll find that it's pretty hard to predict some of the things. But yeah, some of the things you can predict, but some of them you can't. There are other versions of the equation, right? Because some of these properties are hard to predict from that equation. It's not really the nicest form of the equation. So there's another form of the equation, a couple of forms you'll see later on that are even nicer to work with. They allow us to look at a glance at an equation and say, "Ooh, I can tell where the vertex is going to be," or I can tell, certain things about it. All right. So the name of the game for the rest of the assignment when you go to do it is what I'm going to do in the next example. So for A and for B and for C and so on, I want you to make a table of values like we're going to do here, and graph the equation. And then after that, you're going to be able to identify the key features. of the shape that gets graphed. Okay, so let's go through this one. So let's start at 0. And the reason I'm starting at 0 is because the calculation is super easy, right? So for 0, you can just say, like, well, that's gone and that's gone. It's all zeros, 0 times 0 and negative 8 times 0. So you just get an answer of 19. No calculations needed at all. It's just 19. Super easy. Okay. These aren't officially crossed out forever, of course, right? That was just for calculating when x is 0. 19's way off the scale there. So we're going to have to look for some more numbers, right? Possibly out to 10 or possibly out to minus 10. Let's just do sort of the next easiest number, which is a 1. And I'll show the calculation for it. So we have our y equals x squared minus 8x plus 19. And we're letting x equal 1, right? So we're going to have a 1 squared minus an 8 times a 1. And plus a 19. And so we're going to have, obviously 1 take away 8 plus 19. So you could just use a calculator for this completely, or you could easily see like 19 take away 8 is just 11. 11 plus 1 is going to be 12, right? So you get an answer of 12. Right? So I have an answer of 12 there, which is closer to being able to be graphed. In fact, I could graph it, I suppose, where if I went to 1 and I put a dot 2 steps above, right, somewhere around there. But it's off the scale, so I could see why someone might not have graphed it at all. So let's just keep going. Let's graph another one. We're kind of headed in the right direction at least, right? It's a little bit closer to being on the graph. Let's go to 2 next. And for this one, I'm going to show how you could do lots of calculations, but quicker. And, as long as you're able to follow this idea and get the right answers consistently, then you can save yourself some time. If you're finding you're not getting the right answers consistently, then take some more time, show some work, show all the steps, like in this first example where x was 1. So let's put in an x equals 2, right? So 2 squared, you can just be like, well, it's 4. I don't really need to write that. 2 squared is 4. 2 times 8 is 16, so take away a 16, and then plus a 19, right? So now you can just get those values. And this one I could probably do some in my head again here, because 16 taken away from 19 is just 3. 3 plus 4 is 7. Okay? But of course you could do this if you're more comfortable and say, okay, well, I have to just do 4 take away 16 plus 19. And it's going to give me that 7 answer. Okay? So we know the answer is 7, and so we have it in there. So now you can go and do another one. I'm just going to use different colors to illustrate what I've done. Okay, so for doing the 3. So for the 3, we're going to plug in a 3, and 3 squared is 9. 8 times 3 is 24, but certainly check with a calculator if you need to, right? And then you have that. This one, I'd probably just use a calculator instead of having to carry the 1 or whatever in my head, right? So we have the 8 times the 3 just as a double check. There's the 24. So let's have clear that and do 9, take away 24 plus 19. Gives me a 4. So the red one was a 4. Don't have to use different colors, obviously, but I'm just doing it for clarity on my work here. And then let's do a black one. Let's put in the 4. And what do we get from that? So 4 squared is 16. 8 times 4 is 32. So we're going to do that. So let's do the 16, take away the 32, add the 19. We get a 3. Keep going. So let's go to 5. Some room here. So for 5, let's go to a blue. So we got 5 squared, it's 25. We have the 5 times the 8 is the 40. Check with a calculator if you need, of course, right? And the previous one was a 3. Let's put this down here. So we've got 25, take away 40, plus 19. Gives us 4. So we've got a 4 here and a 4 there. And so this is something you're going to watch for with quadratics as you get used to this. You're going to watch for if you can happen to find a spot where it's going up 1 on this side and up 1 on that side. You can tell you found that symmetry spot. So you can actually tell that's your axis, symmetry, x equals 4, right? When we get to the features later on. But I think we can start to graph this now and maybe do one more. But in fact, I'll show you that you don't really need to do any more calculations, really. So let's graph here. We've got the 1 is the 12 we got. The 2 is at 7. I'll put a dot up there for the blue here for consistency. The 3 we're at 4. And then the 4 we're at 3. And at 5 we're at 4. Over 5 and up 4. And now this is where I'm saying you don't really need to do more calculations because you can tell based on the pattern that the next one's going to be a 7, right? Because you can have this leads to that next one being a 7, so I could just do the symmetry. Like if I'm over 1 step I went to there, if I go over 2 steps I go to there, it's going to be the same thing, right? So basically that dot's going to go in based on that same pattern. And finally, even the one up here, if I wanted, I could put that one in too. Okay, so my graph here looks like this. So if you're noticing, it's the exact same shape, just in a very different spot. Right? Same shape as that original one, just in a different spot. So if we're going through our features, we can say, of course, it's same shape. So obviously it's quadratic shape. And you might want to point out that it's the exact same width, etc., as the other one, because it is. What else do we have for features? We had the shape and direction of opening and so on, right? So put in here, it opens up. The vertex, let's label that vertex. Right there, you can tell it's the vertex, and that's at 4, 3, isn't it? So the vertex is at 4, 3. So vertex at 4, 3. Once we have that vertex, it's kind of nice to sort of point out, like, that pretty easy to see the minimum value in this case, right? So it's a minimum because we're going down and up, right? So we had a minimum value, and the minimum value is this height of 3. That's a minimum of y equals 3. And the axis of symmetry, pointed out earlier, right, is that the x equals 4. So axis of symmetry, x equals 4. Don't have to write it in both spots, really. I'm just trying to be clear on my example here. Symmetry, x equals 4. Which, again, notice the 4 matches the 4, and the 3 matches the 3. Right? And was there one more I have there? Oh, x and y intercepts. Right. So x and y intercepts. Well, this one, weirdly enough, notice it doesn't have x intercepts, does it? Right? So this one has no x intercepts. Point that out. Right? No x intercepts at all. The y-intercept, a little hard to see where it would be. Obviously, it's up there somewhere. But on the table, we actually already had that number. So the y-intercept actually had the calculation here for that thing. That's the y-intercept. You might remember from grade 9, for the y-intercept, set x equal to 0. Right? Because it's, you want to be in the middle of the graph in order to be on the y-axis. Right? So I have to be at x equals 0. Well, way up here somewhere, if I were to, I can't really do it because I can't extend the graph that way, but up there at a y value of 19 would be the y-intercept. Okay, so that's every little detail to do with that equation. And again, wouldn't be a bad, I'm always leaving a blank one there. If you're printing this off, you could do work yourself, or you could, and then check the video, or do it as you watch the video, or whatever. The more engaged you are as you're learning this, the more it'll seem really easy to you, which is good. So I'll just do that one for now. I want you to start trying this. This is going to be a more than 1 day lesson, possibly just the 2 days. Certainly with my in-school class, I did the same thing. We just run out of time to do a good job on the rest. But really, I want you to feel you have time to calculate, just like we did for the one just now, for each of these. Okay? And then at the end of all that, you're going to be able to start to pick out the things that you can tell easily from the standard form and the things you can't tell from the standard form. Like in this example here, can you predict some things about the equation so that it'll be the same shape as this one? So same shape as in B, right? The same shape as in B, so same width, same shape, but open down instead and have a vertex in the bottom left quadrant somewhere, right? So can you have the equation that makes the vertex be there and open down and have that same shape? So like, what's the equation for that? There's some stuff you can tell. There's some stuff you'd be able to say, I know it'll be this at least. And then there's some that's just not really possible at this point. And that'll start to come together, especially when we do the graphing using technology stuff. We'll start to tie it all together. All right. So I hope that works for you. That's the practice page there. Yeah. And post some questions if you need any help. All right. Until next time.